Okay, cool. Okay, well, welcome everyone to another TCS Plus talk. We're very happy to have Sumegha Garg from Harvard talking to us about the coin problem with applications to data streams. So before we start, I'll just remind everyone that if you have any questions, you please feel free to unmute yourself and ask. And then next week, we'll have Yang Lu talking to us about algorithms for max flow. But please, Sumegha, take it away.
Thanks for inviting me to talk, and thank you all for tuning in, and thanks Eric for the introduction. So today I'll be talking about a recent work with Mark and David. This is based. This work is on the coin problem with applications to data streams. So the coin problem that we study is defined as follows: you're given a stream of n independently and identically drawn uniformly random bits. That is, you're given a stream. There are n bits that are given to you in a stream x1 to xn, and each xi is plus 1 or minus 1 with each with probability half. And then at the end of the stream, your algorithm needs to output the majority of these n bits. And you need to be correct with high probability over the input distribution, which is the uniform distribution here. Now there's an algorithm that requires just log in space and computes the majority on every input with probability 1. That is, it's a deterministic algorithm. What this algorithm does is it keeps track of the sum of x1 to xi, and this requires log in space. And at the end, looking at the sum or the count, it just sees if the count is greater than 0 or less than 0, and can compute the majority looking at that. Now the question is, can you do better in terms of the space required to compute majority when you only need to be correct? You only need to be correct with high probability, let's say with probability 0.999 over the input distribution, which is the uniform distribution. Any questions in the problem statement?
So the algorithm knows n?
Yeah, it knows n. And at every time step, it knows I. You do not need to store I. You do not need the space to store I. So the coin problem studied in previous works considers the following problem of distinguishing between n identically and independently drawn uniform coins and n independently and identically drawn coins with bias half plus delta towards 1. That is, either you have uniform coins, or you have, where I refer to coins just as bits, or you have coins that are 1 with probability half plus delta and minus 1 with probability half minus delta. And there can be various computation models in which you can study this distinguishing problem. We are studying this problem in the streaming algorithm, streaming model. Now, solving for majority on uniform distribution suffices to suffices to solve this problem of distinguishing for a certain delta, which is theta of 1 by square root n. And for such deltas, we know a lower bound of omega log n. So the best known lower bound for computing majority on uniform distribution is omega log n in the streaming model. I want to mention another work of Hellman and Cover, which proved a strong lower bound of omega log 1 by delta on the memory on the memory when the algorithm is time invariant. That is, it does not know what numbered bit it is reading. It just needs to distinguish between coins, uniform coins versus biased coins. But we want a lower bound, memory lower bound for time variant problems, algorithms, sorry. Okay, so there has been related work on counting. So it is known that when xi's are plus minus 1, then counting which is just like sum of xi within a constant factor of 1 plus epsilon requires omega log n bits, log n memory. And then you will ask the question, why doesn't this answer our question? It is because this lower bound is worst case of the input. That is, it shows that a streaming algorithm that is correct on every input stream, that is approximates the count of every input stream, within a constant factor, but with high probability over its randomness used, is requires omega log n space. But we want to prove an average case lower bound that is that proves lower bounds for streaming algorithms that works with high probability over the uniform distribution. Then I want to mention some related work on majority. So this paper showed that one-sided two-player communication complexity for greater than function is omega log n. And this is when Alice and Bob both have log n bit inputs, and they want to see if Alice input is greater than Bob's input. And through simple reduction, this proves that majority is hard to compute on every input with high probability in less than log n space. Let's go a bit more let's dig a bit deeper in how to prove majority hardness using two-player communication complexity. So such lower bounds work as follows. Alice gets the first half of the stream, that is the n by 2. It has an n by 2 sized input, and Bob gets the second half of the stream, that is it also has an n by 2 sized input. And then Alice, the communication is only allowed from Alice to Bob, and it's a one-shot communication. So Alice sends a message M to Bob, and Bob, seeing this message M and its input stream, it needs to output the majority of these n bits. It is easy to see that a streaming algorithm with memory R gives a protocol for the above problem with message size equal to R. And thus, therefore, communication lower bounds for two-player communication model implies memory lower bounds for streaming to compute the same problem. But such techniques, that is of two-player communication complexity, would not be useful for proving hardness of majority on uniform distribution. This is because okay, so before that, in this model, we again have Alice and Bob having n by 2 bit input, and both of their inputs are drawn from uniform distribution, and then Alice sends a single message to Bob, and Bob needs to compute the majority of the entire input stream, but with high probability over the uniform distribution from which these inputs are being drawn. Now, two-player communication complexity would not be useful for proving hardness on uniform distribution because there is a constant communication protocol that computes majority with large constant advantage. The protocol is as follows. With high probability, Alice input would be, the sum of Alice input would be a constant times square root n, and it just gives, and Alice just sends an approximation of this constant to Bob. And then in the end, this protocol will be, using this protocol, Bob will be able to compute the sum of x1 to xn within with high probability over the distribution within an additive factor of 10 to the minus 4 times square root n. And thus, with such a approximation of the count, it is able to compute the majority with high probability over the uniform distribution. So such two-player communication complexity can only give us order omega 1 memory lower bound on computing majority on uniform distribution. So any questions till now?
Hi, Sumegha. I have some questions about the advantage. I think this is actually related to like a few slides before. So this results are all for, oh, you don't have to go back. Okay. This results are all for like advantage, like 1 over squared n or something. So I'm wondering, like, the people will consider advantage, let's say 1 over n instead.
These results are not for advantage 1 by square root n. It's like a constant advantage. So like
Oh,
you are computing majority with an advantage of say 0.99
I
over
see.
the
I see.
uniform distribution.
I see. I see. Okay. 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 That makes sense. Yeah. And this is only for like computing. So the message is 1 bit also, right? In this case. Um. Yeah. Okay.
In this algorithm, yeah,
I see. I see.
it's
Okay.
like a constant bits.
I see. Okay. Thanks.
Yeah, thanks. Cool. Now, so let's move on to our result. So this is our result. We proved that any one pass streaming algorithm which outputs the majority with at least 0.999 probability over the input distribution, which is the uniform distribution, requires omega log n space. Um, so as Daniel raised a good point, this is so we prove this lower bound against streaming algorithms that computes majority with an advantage of 0.999, and it's some constant that after which we can prove the lower bound. For example, we are not able to prove an omega log n space lower bound for say advantage of 0.7. Okay. So we still use tools from communication complexity to prove our lower bound, but we use an n-party one-way communication model to prove the log n space lower bound for majority on uniform distribution. Next, I will describe the n-party communication model. So here we have n parties. The ith party receives the ith input bit, and the communication is only allowed for party pi to pi plus 1. And it's a one shot communication. That is, the first party sends a message to the second party, and then the second party sends a message to the third party, and then so on. And then in the end, the nth party Pn needs to output the majority bit of the entire input stream. And it is easy to see just by how I described the n-party communication model that any streaming algorithm M can be simulated by an n-party communication protocol. So the party PI sends message MI, which is the memory state of the streaming algorithm capital M after reading I bits to PI plus 1. And knowing the memory state MI minus 1 and its input bit, it is able to compute MI plus 1. And thus it's a valid communication protocol. I would next I would describe this notation. This notation would be used extensively in the rest of the slides. So semicolon B given C represents the mutual information between the random variables A and B conditioned on the random variable C. So to prove lower bounds against streaming algorithms, we define a new notion of information cost for such n-party one-way communication protocols, which are appropriate for proving strong memory lower bounds against streaming algorithms. The new notion of information cost is defined as follows. Here, IC of M, where you can think of M as the streaming algorithm or the corresponding communication protocol associated with it. And I will use both of these descriptions of M interchangeably in the rest of the slides. So information cost of M is given by you sum I equal to 1 from 1 to n, sum j from 1 to I, the mutual information between mi and xj conditioned on mj minus 1. So what is this? This is the mutual information between memory state after reading I bits, the mutual information between this memory state and the jth input bit conditioned on the memory state just before reading the jth input bit. And you then sum over j equal to 1 to I, all the input bits up to the ith level, and then you sum over from I equal to 1 to n. to define any mutual information, you need to define the distribution over of the random variables over which the mutual information is defined. So here X is drawn from uniform distribution over -1, 1 to n, and mi is the random variable denoting the memory state after reading I input bits, and its distribution is dictated by the uniform distribution of on the inputs, and the randomness used by the streaming algorithm M, or the corresponding communication protocol. So this information, just to be clear, this information cost is defined for communication protocols, but it has direct relation to the, we can just write it in terms of the parameters of the streaming algorithm M. Okay, this new notion of information cost is very essential for our proof, and I believe that it can be used for proving lower bounds against other kinds of streaming problems. And so if you have any questions regarding this, please ask.
I have a question.
Yeah.
So your variable X is drawn according to some distribution, according to uniform distribution here, but the protocol itself is not random, is it?
So we can, okay, think of the protocol. The protocol can be random. The protocol can use private randomness, that is at each time step. It can use its fresh randomness, but there is no public randomness.
Yeah, but the information cost will remain
it would
sort
not
of
remain
independent from this private randomness, or
it would not remain independent, but these are the protocols.
Not independent, but that means it will not increase the cost, right? Or...
Yeah, but yeah, correct. But it's important. Yeah, but like okay. So why is it important to think of that? So whatever lower bounds that we prove against information cost only work for algorithms that are either deterministic or use private randomness.
Okay.
If you use public randomness, this information cost might decrease much more than whatever lower bound that we are proving.
Thank you.
Yeah, thanks for the question. Okay, so next I would want to give some intuition behind this information cost. A more intuitive definition of information cost might be that you look at a memory state Mi and look at and understand what is the amount of information it contains about the input stream up to the ith step. That is the mutual information between Mi and X less than equal to I. Now, and then you sum from I equal to 1 to n. And this by chain rule can be it will be exactly equal to mutual information between Mi and the jth input bit conditioned on the input up to the jth level. And we note that this information cost as defined on this page is less than equal to the information cost that is defined on the previous page, as long as M only uses private randomness. So it is possible that we can prove stronger lower bounds against the information cost defined on the previous page than the information cost that is defined on this page, and that is why we use this definition, which can give stronger lower bounds, memory lower bounds for streaming algorithms. Okay. So our main theorem is a variance information trade-off. We prove that for any epsilon greater than 0, there exists a delta such that if the information cost of this streaming algorithm M is less than equal to delta n log n, then the expected variance of the sum of the input bits conditioned on the output of the streaming algorithm is greater than equal to 1 minus epsilon times n. So that is, if the information cost of m is less than equal to delta n log n, then the output, then at the end of the streaming algorithm, seeing the output of the algorithm, we would not be able to estimate the count successfully, because the variance of the input stream conditioned on reaching that outputting that output, that variance is still epsilon. It's still very large. It's almost close to the maximum possible variance. So using this variance information trade-off, we can prove our main result because of the following two bullet points. First, that the distribution of sum of xi conditioned on the output of m, which computes majority with 0.999 advantage, has low variance. So because now the sum has low variance, this implies that the information cost of this protocol should be greater than equal to delta n log n. And then we prove that this information cost is actually less than equal to n times r, where r is the message or memory size of m. So this proves that r needs to be greater than equal to delta log n. That is the memory size of memory required by m is at least delta log n.
Sorry, Sumegha, what should the variance be of a correct estimator? So in this first bullet point.
So like with probability 1, it outputs the majority.
Say, yeah.
So that should be like some constant times n.
I see, but it's constant strictly less than 1.
Yeah. Like it's like, so it's basically like, you can think of it as like the so expectation of xi conditioned on that the sum is greater than 0. So this is like this expectation, this expectation is greater than is around like constant times square root n. So the variance is like so think of it. So this can be, so this thing can be written as expectation of the expectation of xi given m, and given the output of a square of that is less than equal to epsilon times n. So you are basically so the expectation given the output, the expectation should be close to 0, but when you are outputting the majority with probability 1, then the expectation is like all constant times square root n. It is not close to 0. So that's exactly like, because so it's like all the inputs that are reaching that output state are greater than equal to 0. So the expectation of sum of xi is like square root n. Does that make sense?
I see. Yeah, I think so.
Yeah, it's okay. So what I want to say is that like this statement is equivalent to saying that the expectation of the sum xi given the output, like given one of the outputs, like given say 1, is like close to 0. So like given the expectation of the sum given the output should be close to 0, but this is not the case when you are conditioning on the input stream, conditioning on the fact that the sum is always greater than equal to 0. So the expectation of sum of xi conditioned on sum of xi is greater than 0 is like square root a constant times square root n. So which clearly does not satisfy this property. Okay. How much time do I have left, Eric?
So yeah, I would say 35 minutes or so. You have time.
Okay, cool. Okay, so yeah, so yeah, so any other questions?
I have a question about the main theorem. Can you go back one slide?
Yeah.
So does this also imply that we can get the variance of the, like using the there's this law of total variance thing. So can you then, is the goal then to use this to then derive the variance of the majority here, like without
So,
the expectation?
sorry, can you repeat the question?
Like is the goal then to get the, can you get the variance of the majority without the expectation then using the law of total variance? Like is that what is that an implication of this statement too? Because you have the expectation of the variance here, and then you can also get the variance of the expectation. Um,
Variance of the expectation, I'm not sure what that means.
yeah, so like so you're conditioning on the messages M being from MN, and so you get the expectation of the variance here. And so yeah, this is might just be like a result, like it follows from this result actually. I mean, I think. But maybe I can just message you later actually about that.
Yeah, sounds good. Cool. Thanks. Okay. So next, so our main technical result is the lower bound for the coin problem, and then we extend these results to various other problems and which have applications to data streams. So we prove almost tight lower bounds for solving multiple randomly interleaved copies of the coin problem, as well as for solving the OR of multiple copies of a variant of a coin problem. And then we lift these lower bounds to various streaming problems in the bounded deletion model and the random order model. So because we started with proving memory lower bound for majority under uniform distribution, we are we lift these lower bounds to lower bounds in streaming lower bounds for various streaming problems, and we end up with proving hardness of distributions that have nice properties, which are appropriate in proving lower bounds in the bounded deletion model and the random order model. So I would not go into the details of the first bullet point, that is where we extend our coin problem to proving lower bounds for solving k copies of the coin problem or solving OR of k copies of the coin problem. But next I would like to go into a bit of details of the streaming of one of the streaming lower bounds that we prove. So before that, let me describe the streaming model. So a d-dimensional in a streaming model, we have a d-dimensional vector x, which is first initialized at 0 to the d, and then we get a stream of updates, stream of m updates, where each update is of the form xij is updated to xij plus delta j. That is, you are given an index of x to update with delta j, where delta j is in -1, 1. And all the updates are of this form, and then you get m updates. So at every step, you're updating this underlying d-dimensional vector x. And then in a streaming problem, you are usually tasked with computing properties of x at the end of the stream in small space. So this space, what this space is usually like is like of order log d. That is, you want to compute approximations of some property of x in say log d space, which is much less than the space required to store the entire d-dimensional vector X, which is order D space. So for example, let's say L2 norm of X is defined as the sum from I equal to 1 to D xi square. So for example, at the end of the stream, you can be asked to compute the L2 norm of X within an approximation of 1 plus minus epsilon. So the problem that we study is as follows, is called the L2 point query problem. So you are given an index L at the end of the stream, and you want to output XL up to the additive error of epsilon times the L2 norm of X. Any questions with the problem statement?
Quick question, Sumegha. The coordinates of the vector X are just integers? Or are they bits, integers?
Integers.
Okay, so you might need more than space log D to, more than space D to store the vector, or you counted the integers as being
true.
small.
Yeah,
okay.
so let's say poly D comma M.
Okay.
Yeah. But we would be working with much less space than that. We wouldn't be storing the dimension X, vector X. Yeah. So and then we look at this problem in the random order model, where the updates arrive in uniformly random order. That is, the set of updates are fixed, but you have this guarantee that they are arriving in a uniformly random order. That is, think of it as like at every time step, you choose someone chooses an update from a given set of updates and gives uniformly at random, and then gives you that update. And then the goal in this model is to output correctly with high probability over the private randomness and the order of updates. This is so what is known for this L2 point query problem? We know that you can compute the you can solve this problem in space order log MD by epsilon square, and such an algorithm is correct on every set of updates and every sequence of updates with high probability over the randomness used. And then in this model, where you need to be correct on every sequence of updates, that is every order of updates, there is a lower bound of omega log m by epsilon square against streaming algorithms that needs to be correct on every sequence of updates. Now the question is, if you need to be correct only in the random order model, can you do better in terms of space? So we show that this is not possible. That is, any streaming algorithm which in the random order model solves the L2 point query problem with sufficiently large constant probability requires omega log m by epsilon square bits of memory. So to contrast our lower bound, we also prove that we also give an algorithm that that in the insertion only model, along with the random order model, solves the L2 point query problem using much less space, that is log m plus 1 by epsilon square memory. So we prove lower bounds for various streaming problems, but the gist is that where for these streaming problems, we only knew lower bounds in the Turnstein model. That is the worst case model. That is, you need to be correct with high probability in the worst case. We are able to prove matching lower bounds in the bounded deletion model and the random order model because we started with proving the lower bound on majority on a nice distribution. So the bounded deletion model is just that you have the promise that the updates are of the form that at every time step, the L2 norm of L2 norm of X at that time step does not drop more than alpha times the L2 norm at any time step before that. Okay. So any questions for the streaming problems? Because next I will move to the proof outline. Cool. Okay. So even if I lost you somewhere there, you can just start listening right now. Here we will just concentrate on this variance information trade-off and then try to see how to prove such result. So to reiterate, our various information trade-off showed that for any epsilon, there exists a delta such that the information cost of a streaming algorithm M, if it is less than delta n log n, then the expected variance condition, the output of the streaming algorithm is very close to the maximum possible. So to prove such result, we look at the input stream and we divide the input stream for every ith step. We divide the input stream into log n scales and prove roughly that a memory state mi needs to remember omega 1 bits for every such scale to estimate the count successfully in the end. So if you can prove such a statement, when you sum over the number of scales and sum over I equal to 1 to n, you are able to prove that the information cost of M is at least omega n log n. So let's see what do I mean by you divide the input into log n scales. It's something like this. So ideally, you want to prove that first that the mutual information between mi and input and the ith input bit conditioned on all the input bits all the input bits up to the I minus 1 step is omega 1. And then you look at the previous 2 bits, and then you want to say that the mutual information between mi and the previous 2 bits conditioned on the bits and bits up to the I minus 3 level is omega 1. And then you look at the 4 bits and then 8 bits before that. And then you want to prove that for all these log I scales, the mutual information between mi and that scale is omega 1. So to get an intuition of why such a statement, we would want such a statement is that if mi is keeping count of the sum of xi, then such a statement is true. When such a statement is true when xi, when the distribution of xi is uniform distribution, x is uniform distribution. For example, given x less than I, if xi is sum of if mi is sum of x1 to xi, then given x less than I, it exactly knows what xi is. So this first thing is 1. And then you can see that under uniform distribution, these will also be constant time, would also be constant. And then by chain rule, if you are able to prove such a statement, this would prove that the mutual information between mi and x less than equal to I is omega log I. So in fact, we are able to prove such a variant of such a statement for deterministic algorithms and when we sum from I equal to 1 to n, you get that the information cost that the second definition of information cost, with respect to that definition, the information cost is at least omega n log n. But for randomized algorithms, this isn't true. So when M is allowed private randomness, we, instead of conditioning on the input stream up to the i-1th level, we conditioned on the memory state after reading the first i-1 bits. And we show a variant of the following statement. That is, the mutual information between mi and ixi condition on mi-1, and then you look at the previous 2 bits, and then you look at the previous 4 bits, and so on. They are all omega 1. And then summing over the scales and summing over I, we are able to prove that the mutual information, the information cost with respect to the first definition is omega n log n, even for algorithms that use private randomness. Any questions till now? Okay, nice. So next we will look at, so till now we have talked about how we divide the input stream into scales for each ith step. Now let's look at how to prove an omega 1 lower bound on the mutual information between mi and one of these scales. So for this, let's look at a scale of size 2 to the j. And then we divide the input into t equal to n by s blocks. So that each block has s bits of the input stream, and let s1 to st denote their sum. That is, s1 denotes the sum of the first s bits of the input stream, and then s2 denotes the sum of the second set of s bits of the input stream, and so on. And then we want to say that we look at the variance of this sum conditioned on the memory state after the ith block. So we look at the variance of si conditioned on the memory state after the ith block and the memory state just before reading the bits in the ith block. So we want to say that if this variance of the sum conditioned on these memory states is just epsilon less than the maximum possible, then this memory state after the ith block needs to have some omega 1 bits of information about the sum of bits in the ith block. This is not that hard to prove. But what is interesting is that this is just, we can go further. We can show that this memory state after reading the bits in the ith block has omega 1 bits of information about the first 1 minus alpha fraction of the inputs in this ith block. So this means that once you look at a block and look at the sum of the input bits in that block, now if the memory state after this ith block has information about the sum, then it needs to have information about the first 1 minus alpha fraction of the inputs in that block too. It is not possible that you can have information only about the last alpha fraction of the inputs in this block and the sum. So the main gadget in our proof is this statement that if the variance of the sum conditioned on the memory states before and after the block is less than 1 minus epsilon times the maximum, then this memory state after the ith block needs to have omega 1 bits of information about the first 1 minus alpha fraction of the inputs in that block. So then using this, oh, sorry, someone raised hand.
Yeah, quick question. So could you go back for a second? The statement in red, do you prove that only assuming that M outputs the correct majority at the very end, or do you have to make any intermediate assumptions as well?
Yeah, we will see in the next slide. You only need that it outputs in the end because we will see because these variances add up due to independence.
Okay, thanks.
Yeah, good question. Thank you. So then if let's see. So if now if your block size was S was equal to I, then this statement, then you have let's just look at the second statement and assume that the first statement is true. Then you have proved that that Mi needs to remember it needs to have omega 1 bits of information about the first 1 minus alpha fraction of the input stream, right? And then you look at, you change your size of the block to the next scale would be alpha times S. Instead of S by 2, it is alpha times S. And then you again use this theorem to prove that now Mi needs to have omega 1 bits of information about the 1 minus alpha fraction of the first starting 1 minus alpha fraction of the input stream in this block of size alpha S. That is you have proven that Mi has omega 1 bits of information about the 1 minus alpha fraction. Then you prove 1 minus alpha fraction of the remaining input stream, and so on. So your scale is not being divided by 2, but it is being multiplied by a factor of alpha, which is much less than 2. But still it gives constant times log I lower bound. So then now summing over the scales, you can prove that Mi needs to have log I amounts of information about the starting about the input stream up to ith level. So now let's look at the first statement. Here we want to, this information lower bound is only true if the variance of Si given MIS is less than 2j times 1 minus epsilon. So our claim is that this variance cannot be high for many such blocks, because as the SIs, which are the sums, are independent, conditioned on these intermediate memory states, the variances add up, and we can show that if we have low variance conditioned on the output of the streaming algorithm M, this implies that the variances cannot be, these variances cannot be high for many such blocks, which further implies that you have high information, you have high mutual information for many such blocks at this scale. So this is basically this, and then you add up the scales and you finally get the required variance information trade-off. Okay, any questions? Cool. Okay, so this is all I would like to say about the proof and our result. Next, I would want to mention a couple of open problems. So reiterating, in the streaming model, we proved that lower bounds of memory lower bounds of log m by epsilon square for solving the L2 point query problem in the bounded deletion model and the random order model. And then we also showed an algorithm for the L2 point query problem in insertion only model with randomly ordered updates that takes much less than log m by epsilon square memory. Now the question is, what is the space complexity for solving the L2 point query problem in the insertion only model, but the turnstile model? That is, when your updates can only be of the form xij plus 1, but you and you want to prove lower bounds against or find upper bounds for a streaming algorithm that solves the L2 point query problem with high probability over any sequence of updates. If the sequence of updates is random, we can already show that you can do it in much better memory than that is required for when it is not an insertion only model. Okay. And then second of the open problems is which I find very interesting is in the world of coin problem. Here the question is, can we prove better lower bounds than omega log n on memory for the coin problem in the streaming model for say delta equal to n to the minus 0.4. So we proved a lower bound of omega log n when delta is some small constant times n to the minus 0.5. And then you have upper bounds of omega log 1 by delta for much larger values of delta, but we do not know anything about what about this values of delta, which is like n to the minus 0.4. Okay. Any questions on the open problems? Okay, cool. I'll be happy to take more questions, and thank you very much for listening to my talk and the questions.